In this video, we're going to discuss more about the relationship between ideals and varieties. And basically what we're going to do is prove lemma 7, which says that the ideal generated by the polynomials f sub 1 through f sub s is always a subset of the ideal of the variety defined by the polynomials f sub 1 through f sub s. And of course, this set can be larger in the sense that it contains polynomials that this set does not contain. We're going to prove that. And then we're also going to prove proposition 8, which deals with the set inclusions between varieties and their corresponding ideals. So if all of the points in one variety also belong to another variety, like this, it turns out that all of the functions that are equal to 0 on this variety are also equal to 0 on this variety. And the two varieties are equal if and only if their ideals are equal. And then we'll look at a few questions about ideals. Now, this first lemma is motivated by the last example that we did. In the last video, we showed that the ideal of the variety given by the polynomials y minus x squared and z minus x cubed, that's our twisted cubic, turned out to be equal to the ideal generated by the two polynomials y minus x squared and z minus x cubed. Now you may have forgotten what these objects mean, so I will elaborate on those again in general. So let's say you start with polynomials, f sub 1 through f sub s, from some polynomial ring with coefficients in the field k and the variables x sub 1 through x sub n. If you take those and set those equal to 0, that gives you a system of polynomial equations. So you have f1 equals 0, f2 equals 0, all the way through f sub s equals 0. Well, the solution set of that system of equations is a subset of n-dimensional affine space, and we call that the affine variety V. So I've written it like this, but remember what that is again. It's a solution set of the system of S polynomial equations. Now, a solution set might be a list of points. There might be a finite number of points where all these polynomials are equal to 0. If that's true, we would like to be able to list them. Now, sometimes the polynomials are all equal to 0 along a curve or along a surface or along a hypersurface. All of those would be affine varieties as well, as we've seen. Now, once we have an affine variety, that is a set of points that is, again, a solution set to a system of S polynomial equations, we can think a little bit differently. We started with polynomials over here. We can actually go back to polynomials if we talk about the ideal of that variety. Now remember what an ideal is. An ideal of a variety is the set of all polynomial functions in that polynomial ring in the variables x sub 1 through x sub m with coefficients in the field k, such that those polynomials all vanish at the points of V. So this is the set of all polynomials that are equal to 0 when we're on the affine variety V. Now, we already know that by definition, f1 is equal to 0, f2 is equal to 0, f sub 3 is equal to 0, f sub 1 through f sub s are all equal to 0 on the variety v. That's how we're defining v in the first place. We're saying it's a set of all points for which these polynomials are 0. The ideal of the variety includes all of those polynomials, but we're also saying, are there any other polynomials that are also equal to 0 when we're on that set in n-dimensional affine space? If so, those other polynomials are going to be in this set too. Now you might be saying, okay, well, how does that relate to this? Remember what this is. This is called the ideal generated by the polynomial functions y minus x squared and z minus x cubed. In general, an ideal generated by polynomials f sub 1 through f sub s is denoted like this. And this is the set of all polynomials of this form, h1 times f1 plus h2 times f2, all the way through h sub s times f sub s, where the h sub I are all just generic polynomials in our polynomial ring. And of course, we tend to simplify that notation rather than writing out that sum. We don't have time for that. We're just going to write this instead. It means the same thing. This is called the ideal generated by the polynomials f sub 1 through f sub s. And the way you want to think about this is, well, I'm going to pose it to you the same way that the textbook author posed it to you, and then I will pose it to you the same way that I rephrased it for myself. The textbook authors said, this is the set of all polynomial consequences of these polynomials here. And if you're saying polynomial consequences of polynomials, what on earth does that mean? It's really related to this system of polynomial equations. If I'm thinking of all of these polynomial equations being satisfied, so all of these functions are equal to 0 at the same time, and I take the first equation and I multiply it by h1, and I take the second equation and I multiply it by a polynomial h sub 2, and I take the s equation here, the s equation, and I multiply it by h sub s, and then I add those all together. Since all of these polynomials are 0, when I multiply by other polynomials and add them together, I'm still going to get 0. So the ideal generated by f sub 1 through f sub s is the set of all polynomials that must be 0 if this system of equations is satisfied. Okay, so we've got these four different forms that are all related to each other. We have a system of polynomial equations, and then we have the affine variety. That's the solution set of that system in n-dimensional affine space. And then we have the ideal of the variety. This is the set of all polynomials that are equal to 0 on this set in n-dimensional affine space. And then we have the ideal generated by these polynomials, which is the set of all polynomials that must be 0 if those polynomials, the generating polynomials, are equal to 0. In other words, these are the polynomials that must be 0 if the original system of equations is satisfied. And that's what the textbook authors mean when they talk about this ideal being the polynomial consequences of the original system or of the original polynomials. It's the consequence. These are the polynomials that must be 0 if these polynomials are 0, which does not have as nice a ring to it as the set of polynomial consequences of the other polynomials. But I think this, at least for me, makes more sense. So I just wanted to rephrase it for you that way. Excuse me. And then we proved earlier that this was an ideal. Now, last time we said that the ideal of the variety generated by y minus x squared and z minus x cubed, and that was our twisted cubic. Now remember, again, this is the set of all polynomial functions that are equal to 0 on the twisted cubic. Turns out to be the same as the ideal generated by the two polynomial functions y minus x squared and z minus x cubed. So in this particular case, the ideal of the variety generated by f sub 1 and f sub 2 is equal to the ideal generated or the ideal generated by f sub 1 and f sub 2. So the question is, is this true in general? Is it true in general that the ideal of the variety generated by defined by the polynomial functions f sub 1 through f sub s is equal to the ideal generated by the polynomials themselves? Is this set always equal to this set? And it turns out that they're not equal to each other in general, but this set is always a subset of this set. Or in other words, these polynomials, the set of polynomial consequences, the set of polynomials that would all have to be 0 if the original polynomials were 0, all of those polynomials have to belong to the ideal of the variety generated by those polynomials or defined by those polynomials. But there may be some other polynomials in this set that don't belong in this set. That's what lemma number 7 says. There are polynomials in here. Every single polynomial in here is in here, but there may be some in here that are not in here. And that's what that, although equality need not occur, means. So we're going to prove lemma number 7 now, and then we'll look at proposition 8, and then we'll talk about 3 questions about ideals. And we're not going to answer many of those questions until chapter 4. We're at the very end or getting close to the end of chapter 1, but we need some tools from chapters 2 and 3 to really flesh out this relationship between ideals and varieties. So we are really just getting started with the relationship between ideals and varieties here. But as we learn more about Grosvenor bases and more, we're going to be able to talk more about that relationship. So let's prove lemma number 7. So lemma 7 says that if f sub 1 through f sub s are polynomials in our polynomial ring, then the ideal generated by the polynomials is always a subset of the ideal of the variety defined by the polynomials. And then it says, although equality need not occur, in other words, there are some cases where this is strictly larger than this. And when I say strictly larger, I just mean that there are polynomials that belong to the ideal of the variety here that do not belong to this particular ideal. This is a relatively easy result to prove. So we're assuming that we have some polynomials in our polynomial ring, and if we want to show that this set belongs, or this set is a subset of this set, we just need to start with a polynomial that belongs in here and then show that that polynomial would also have to be in here. So this is going to be a very short proof, easy breezy. So we'll assume that f is in the ideal generated by the polynomial functions f sub 1 through f sub s. Then by definition, remember f would have to equal the sum as I goes from 1 through s of h sub I times f sub I where the h sub I are just any polynomials in our polynomial ring. Well, actually, for a particular f, they're going to be specific polynomials in our polynomial ring. So, yeah, we said generic, but it's not generic in general, or it's not generic in this specific case. So we said if f is in this set, then by definition, it can be written this way, where the h sub I are given or specified polynomials in the ring. Now we want to show that this has to belong to the ideal of the variety defined by f sub 1 through f sub s. In order to do that, let's just say that A is a point in the variety V. Well, if A is a point in V, then f sub I of A is equal to 0 for I equals 1 through s. By definition, if A is in V, then all of these polynomials must be 0. So if I substitute A into this polynomial, which is in the ideal generated by f sub 1 through f sub s, well, then all we're going to get is this. Just substitute the A into the h sub I and into the f sub I. And f sub I of A is 0. So this is just the sum of s zeros. Add them together and you're going to get 0. So if A is in V, then f of A is equal to 0. So since we just chose any A in V, f of A is going to equal 0 for all A in V. So that means that f must belong to the ideal of the variety. Easy breezy. Now, to prove this last part, which says although equality need not occur, all we have to do is come up with a counterexample. I'd like to just state for you an example where the ideal generated by some polynomial functions is a subset of the ideal of the variety given by or defined by those functions, but there are some members of this ideal that do not belong to that ideal. So we're just giving an example that proves that equality need not occur. And this is straight from the book. So if you have the book, you've seen this before. Let's consider the variety given, or the ideal generated by the polynomials x squared and y squared. Well, by definition, this is the set of all polynomials that can be written this way. And where h1 and h2 are polynomials in some polynomial ring in the variables x and y. So let's just assume that our field is the field of real numbers. So we're here. Excuse me. Now, if I were to just look at the ideal of this variety, or excuse me, not the ideal of this variety, the variety now generated by the polynomials x squared and y squared, this is going to be the set of all points xy in R2, such that x squared is equal to 0 and y squared is equal to 0. Well, we know that x squared and y squared are only equal to 0 in R2 when x is equal to 0 and y is equal to 0. So that's a single point in two-dimensional space. These would have to be 0 at the same time for both of these to be 0 at the same time. So the variety actually consists of the point 0, 0. That's it. If I were to graph it, it'd be a pretty boring graph. It's right there. That's my variety, a single point. Now, if I look at the ideal of the variety, remember what this is. This is the set of all functions, or all polynomial functions, in our ring of polynomials with coefficients in the reals in variables x and y, such that f of a is equal to 0 for all a and v. But all a and v is a single point. So in other words, this is the set of all polynomial functions for which, f of 0, 0 is equal to 0. So all the polynomials that are equal to 0 at this point. The question is, are there any polynomial functions that are equal to 0 at the origin? Are there any polynomial functions that are equal to 0 right here that don't belong to this set? Well, I think yes. Here's an example. X has to be a member of this ideal, because obviously x is equal to 0 when x and y are both 0. But I claim that x is not a member of this set, because it does not matter which polynomial you choose from this polynomial ring. If you take that polynomial, and you multiply it by x squared, every term in the resulting polynomial will have a degree that is at least 2, because we're taking even the constant term of this and we're multiplying it by x squared. We're not going to have just an x term here. Now, if you're saying to yourself, well, what if it had this h sub 1 had a 1 over x in it? The 1 over x and the x squared could give you the x. Remember, h sub 1 is a polynomial. It's not a rational function, so we're not going to have a 1 over x anywhere. So we've got that over here. And then over here, the same is true. I've got a polynomial times y squared. There's no way that I can take a polynomial and multiply it by y squared and get x. So this cannot be x and this cannot be x. And there's no way I can add a couple of polynomials together that cannot be x and get x. So this x is a member of the ideal of the variety, because x is equal to 0 at the point x equals 0, y equals 0. But x does not belong to this set. X is not in the ideal generated by x squared and y squared. And I think you can see the problem. It's because this is squared. X squared belongs to this, but x doesn't. It turns out that the ideal of the variety defined by the functions x squared and y squared is actually equal to the ideal generated by the polynomials x and y. And this ideal generated by x and y is strictly larger than this ideal generated by polynomials x squared and y squared. The powers are the problem, because these functions are equal to 0 when these functions are equal to 0. But I can't get, well, there are functions that are simpler than this, like these, x to the first, y to the first, that are equal to 0, that don't belong to this set. They don't belong to a set that looks like that. So hopefully that will give you some intuition for maybe the relationship between this and this in general. But we're not going to prove that yet. We're going to talk about the relationship between this and this a little bit later, after we learn a little bit more. But for now, we have the one result, lemma number 7, that says that if you have some polynomials f sub 1 through f sub s in the polynomial ring, then the ideal generated by those polynomials is always a subset of the ideal of the variety defined by the polynomials. But the ideal of the variety could be strictly larger, and you can kind of see why it has nothing to do with those exponents. Now we'd like to prove proposition 8. So let's think about two affine varieties now. So you've got two sets of polynomials. You're setting both of those sets of polynomials equal to 0, and you're finding their solution set. This is a solution set of one set of polynomials. This is a solution set of a different set of polynomials. These could both be finite sets. It could be lists of points, or you might be dealing with a curve or a surface or a hypersurface in n-dimensional affine space. And then we're saying, okay, if all of the points from one affine variety are in the other affine variety, then their ideals have this relationship, and the two affine varieties are equal if and only if their ideals are equal. So we're going to prove this first, and I think the second one is pretty obvious just from the first one, but we'll just talk about what that second point means. So let's prove proposition 8 now. So we have affine varieties, V and W, in n-dimensional affine space. V being a subset of W implies that the ideal of W is a subset of the ideal of V, and vice versa. If the ideal of W is a subset of the ideal of V, then V is a subset of W. And then if the ideals, or if the varieties are equal, the ideals are equal. Okay, so let's prove this. It's actually pretty simple as well. So let's go this way first. So we're first going to show, or we'll show, say that we'll show that V being a subset of W implies that the ideal of W is a subset of the ideal of V. So remember, these are points and these are polynomials. Okay, so let's assume this. Simple proof, direct proof. Assume that V is a subset of W. And remember what that means. That just means that if you have a point A that's in V, then you automatically know that that point is in W because they're subsets of each other. That's what a subset is. And then we're going to say, okay, we're assuming that this is true. Now assume that you have a polynomial function in the ideal of W. So let's suppose that we've got a polynomial in the ideal of W. Well, remember what that means. The ideal of W is a set of polynomials that are all equal to 0 for every point of W. But since every point in W is also a point in V, or wait, that's not what I meant. Since every point in V is also a point in W, the fact that these this function is equal to 0 at all the points of W implies that that function is equal to 0 at all the points of V. Because all of these points that are in W are also in V. Oh gosh, I keep saying it wrong. All the points that are in V are also in W. So that means that F has to be in the ideal of V as well. I hope that makes sense. Since every point in V is also in W, when we say that this polynomial is equal to 0 for all the points of w, that implies that that function would have to be 0 for all the points in v. And if that function is equal to 0 for all the points in v, then it is by definition in the ideal of v. So that means that this set is included in this set. Easy breezy. Now let's go the other way. So let's assume that the ideal of w is a subset of the ideal of v. And by definition, what that means is that if f is in the ideal of w, then f is in the ideal of v. And remember what this means. This is saying that f of a is equal to 0 for all points in w. And then this is saying that f of a must be 0 for all points in v. Now, to show that v must be a subset of w, let's assume that w is generated by g sub 1 through g sub t. So let's say w is the solution set of, g1 equals 0, and g2 equals 0, and g3 equals 0, all the way through g sub t equals 0. Then obviously, g sub 1 through g sub t, if those are all equal to 0, then they have to belong to the ideal of w. So by definition of w and the ideal of w, g sub 1 through g sub t must belong to the ideal of w. And since the ideal of w is a subset of the ideal of v, that means that g sub 1 through g sub t must be in the ideal of v as well. Well, if they're in the ideal of v, then that means that all of these are equal to 0. For all points, or at all points, a and v. Well, if they're equal to 0 at all points a and v, and w consists of all of the points where these polynomials are equal to 0, then v must be a subset of w. Okay, so we showed that if v is a subset of w, the ideal of w is a subset of the ideal of v, and vice versa. And that's the second part here. And that's it. Now I think it's obvious. I'm not even going to write it down because it's so obvious that we could easily switch the roles of v and w. If v is a subset of w and w is a subset of v, well, then they're equal to each other. And that means if v is a subset of w, then this inclusion is true. If w is a subset of v, then you would just flip that. The opposite inclusion would be true. So these would be equal and these would be equal. It's, I think, so obvious that it's not even worth writing down. Okay. That's pretty much it about ideals for right now. We're going to talk more about ideals later. There's a lot more to the relationship between ideals and varieties, but we're going to talk more about that after we get some more background in chapters 2 and 3. When we get to chapter 4, we'll come back to this. It turns out that there are strong geometric implications that relate these ideals and varieties to each other. When I studied this in the past, chapter 4 was my favorite chapter. I got really excited about the results there, and I can't wait to share that with you, but we've got to get some tools under our belt before we get to chapter 4. So let's talk about some important questions related to ideals and varieties. So here are 3 questions. About ideals in the polynomial ring that we're referring to. Here's the first one, the ideal description. We might want to know the answer to this question. Can every ideal is a subset of that polynomial ring be written as the ideal generated by a particular set of polynomial functions? So that's an important question. The next important question is dealing with ideal membership. If we have some polynomials from our ring, we might want to know, is there an algorithm to decide whether F belongs to the ideal generated by F sub 1 through F sub S? And it turns out the answer is yes. And this last one's called Nullstellensatz. I'm sorry if I'm mispronouncing that. Nullstellensatz. We'll talk more about where that name comes from later. If we have some polynomials, we might want to know, what is the exact relationship between the ideal generated by the polynomials and the ideal of the variety defined by the polynomials? Now, we already know that this one is a subset of this one, but we'd like to be able to say something more. Like, it'd be nice to be able to write down a formula for this given this, or a formula for this given the polynomial functions f sub 1 through f sub s. And if we are careful about the field that we choose, it turns out there is a relationship that we can write down after we know a little bit more math. So that's the plan. That's where we're going. We're going to take what would seem to be a detour next time. We're going to talk about polynomials of one variable and the division algorithm. Might not sound that exciting. Like, I know the division algorithm with polynomials, but it's really important when we get into sort of a generalization of that division algorithm for polynomials involving n variables. So we're going to talk about that next time. That's the temporary end of the discussion of ideals, and we'll sort of bring all of this together as we continue through the material.